Have you ever looked at a complex neural signal, perhaps from an electroencephalogram or an array of microelectrodes, and felt overwhelmed by its sheer volume and intricate noise? Making sense of these vast, multidimensional datasets is a fundamental challenge in neurotechnology, where clear patterns are often hidden amidst a sea of correlated variables and unwanted artifacts. Principal component analysis, or PCA, offers a powerful solution by systematically transforming this high-dimensional data into a smaller, more manageable set of uncorrelated variables known as principal components. The core steps involve standardizing your data, computing the covariance matrix, performing eigenvector and eigenvalue decomposition, constructing a feature vector, and finally, projecting your original data onto these new dimensions. These steps are crucial because they allow us to effectively distill the most significant information from noisy or complex signals. Standardization ensures that all features contribute equally to the analysis, preventing variables with larger scales from dominating the outcome. The covariance matrix then precisely quantifies the relationships between different variables, revealing how they move together. Decomposing this matrix into its eigenvalues and eigenvectors is the heart of PCA, as eigenvalues indicate the amount of variance explained by each principal component, while their corresponding eigenvectors define the direction of these new orthogonal axes. To put this into practice, you first prepare your dataset by centering each feature to a zero mean and scaling it to unit variance. Next, you calculate the covariance matrix from this standardized data to capture the linear relationships between all pairs of variables. Then, you compute the eigenvectors and eigenvalues of this covariance matrix. With these, you sort the eigenvalues in descending order and select the top k eigenvectors corresponding to the largest eigenvalues, forming your feature vector. Finally, you use this feature vector to transform your original standardized data into the new, lower dimensional space, effectively creating your principal components. This systematic approach is what makes PCA so valuable for tasks like artifact rejection in neural signals. By identifying and removing components that primarily capture noise, such as eye blinks or muscle artifacts, it allows neuroscientists to isolate and focus on the underlying brain activity with greater clarity. Moreover, the ordered nature of principal components means that the first few often encapsulate the most significant variability in the data, providing a concentrated view of its essence, which is incredibly useful for visualization and further analysis without losing critical information. Ultimately, by following these structured steps, PCA enables researchers and engineers to cut through the complexity of neural signals. It helps reveal the fundamental patterns and structures that might otherwise be obscured, paving the way for more accurate interpretation, efficient data processing, and robust model development in the exciting field of neurotechnology.